Hello everyone. Welcome to this video on learning mathematics through concepts and examples. Today we are going to look at some of the example problems on application of derivatives. Okay, here comes the first example. Verify that Rolle's theorem can be applied to the function f of x equal to x cubed minus 11x squared plus 38x minus 40 on the interval negative 2 through 5. Then find all values of c such that the derivative of the function at c is equal to 0. Okay, so first of all, our function is f of x is equal to x cubed minus 11x squared plus 38x minus 40, which is defined for the x values in the interval from 2 through 5. So this is a polynomial function. So what we know is the polynomial function is continuous everywhere. So the function must be continuous, okay? The function must be continuous in the closed interval from 2 up to 5. And also the polynomial function is differentiable. So definitely this function is also differentiable on the open interval. So f of x is differentiable on the open interval 2 through 5. And what we know is, since both these conditions are true, we can apply the Rolle's theorem. So Rolle's theorem can be applied. So we can say, so Rolle's theorem can be applied. Okay, Rolle's theorem can be applied. But these two conditions are not just the full conditions. In fact, you also need to check one more thing, then only we can confirm that the Rolle's theorem can be applied. So the other thing that we want to see is, I also want to add them here. We can find the value of the function at the endpoint, like f of 2 and f of 5. These two values should also be true, then only we can guarantee that the theorem can be applied. Okay, just these two conditions are not sufficient, so we are going to check these two also. So now if you plug in 2 into this function, it will be 2 cubed minus 11 times 2 squared plus 38 times 2 minus 40. If you simplify this, you'll get 0. Similarly, if you plug in 5 into this function, it will be 5 cubed minus 11 times 5 squared plus 38 times 5 and then minus 40. And if we simplify, this is also 0. In fact, because of these 4 conditions being true, I would say 3 conditions. These two are the first 2 conditions. And the third condition is the value of the function at the endpoint is the same. So since these 3 conditions are true, we can say that the Rolle's theorem can be applied. And once the Rolle's theorem can be applied, the theorem guarantees that there is a point where the derivative of the function is equal to 0 and that c is in this interval. Okay, so let's work on that. Now, by Rolle's theorem, what we know is the derivative of the function at c is equal to 0, where c is a value in that interval or in the interval that is given there. So let's find the derivative of this function and plug in c. So if we find the derivative of x cubed minus 11x squared plus 38x plus 40, it would be 3x squared minus 22x plus 38. But if you plug in c, it will be 3c squared, okay, 3c squared minus 22c plus 38 equal to 0. Now, this is a quadratic equation. We can solve this using quadratic formula. So the value of c will be, c is equal to, if you use the quadratic formula says negative b. So negative of negative 22 here, that will be positive 22, plus or minus the square root of b squared, which is negative 22 squared, b squared, minus 4 times a is 3, c is 38, 4ac. Okay, and we have to divide all this by 2 times a, so 2 times 3 is 6. Okay, we need to simplify this and find the value of c. So I'm going to do it here at the side. So this implies c is equal to 22 plus or minus, if we simplify this one, negative 22 squared minus 4 times 3 times 38, that will be 28. You can use your calculator to simplify that. And we divide that by 6. So that means C is equal to, you can see we have 22 over 6. 22 has a denominator of 6. Then plus or minus square root of 28 is 2 root 7 over 6. So we get C equal to finally 22 over 6 can be reduced to 11 over 3. 11 over 3 plus or minus square root of 7, and then 2 over 3, 2 over 6 is 1/3, so divided by 3. So these are the two values of C that satisfies the condition, or that meets the condition of the Rolle's theorem. So this is how we can use Rolle's theorem. Okay, remember, for the Rolle's theorem to be used, okay, or we can say that the Rolle theorem can be applied if the function is continuous on the closed interval, differentiable on the open interval, and the value of the function at the endpoint are the same. Okay, that's our first example, which was on Rolle's theorem. Now, let's move on to example 2. Here is our example. Verify that the mean value theorem can be applied. Now, this question is on mean value theorem. Previous question was on Rolle's theorem. This is on mean value theorem. Verify that the mean value theorem can be applied to this function on the interval 0 through 1. Then find the value C in the interval that satisfies the conclusion of the mean value theorem. So here our function is f of x equal to x raised to 2/3, and x is in the interval from 0 through 1. That is our interval of interest. So this one is a power function which is continuous everywhere and differentiable everywhere. So we can say that f of x is continuous on the closed interval from 0 through 1, and f of x is differentiable. Okay, f of x is differentiable on the open interval 0 through 1. So meaning of that is, if these two conditions are true, then we can say that the mean value theorem can be applied. So meaning of this is mean value theorem can be applied. So we can apply the mean value theorem once these two conditions are true. So let's see how we can use the mean value theorem. Now what we know is mean value theorem says the derivative of the function at C is equal to f of b minus f of a over b minus a. That is what we know from the mean value theorem. Now the derivative of this function, if we find the derivative, we bring 2/3 in front. So it will be 2/3 x raised to 2/3 minus 1 will be negative 1/3. So the derivative will be, okay, 2/3 x raised to negative 1/3. But here we want derivative at c. So meaning of that is it will be 2/3 c raised to negative 1/3 is equal to f of b. So this is your a is 0, b is 1. So if you plug in 1 into this function, it will be 1 raised to 2/3, which is 1. 1, then minus f of a. If you plug in 0, that will be 0 over b minus a. b minus a is 1 minus 0, which is also 1. So now the meaning of that is c raised to 1/3 is equal to 3/2. Okay, if we multiply on both sides by 3/2, we get c raised to negative 1/3, by the way, negative 1/3 equal to 3/2. So now you can solve this by any method you want. All you need to do is solve that equation and find the value of c. So we can write like this: c is equal to 3/2. If you want to undo this power negative 1/3, you have to raise the power negative 3 on both sides. So it will be 3/2 raised to negative 3, which is same as 2/3 raised to 3. So meaning of that is the value of c is equal to 2 over 3 cubed. 2 cubed is 8 and 3 cubed is 27. 8 over 27. So that is the value of c guaranteed by the mean value theorem, which lies in this interval from 0 through 1. And you can see that 8 over 27 is a number more than 0, but less than 1. So that is the value guaranteed by the theorem. So this is how we can use mean value theorem to solve the application problem like this one. Okay, time for example 3. So in this one, find the open intervals on which the function is increasing or decreasing. That is the first part. And once you do that, you have to find the local maximum and minimum value of the function. So for the function to be increasing, the derivative must be positive. And for the function to be decreasing, the derivative must be negative. So what we are going to do is first we are going to find the derivative of the given function. So here, the function is f of x equal to negative 3x squared plus 4x plus 1. So the derivative would be f prime x equal to, if you use the power rule, that will be negative 6x. Derivative of 4x is 4. And derivative of 1 is 0. So that is the derivative of the function. So for the function to be increasing, let's do where it is increasing. For the function to be increasing, the derivative must be positive. So meaning of that is 6x plus 4 must be greater than 0. And by solving this, we can solve it like this. 6x is greater than, if you subtract 4 on both sides, negative 4. And in order to find the value of x, we can divide on both sides by negative 6. And by dividing by negative 6, the inequality sign will flip, and it will be negative 4 over negative 6, which is 2/3. So meaning of that is the function is increasing, okay? Function is increasing for x is less than 2/3. I'm going to show that on a number line here. If we look at this function carefully, this is a quadratic function. It is defined for all values of x from negative infinity up to infinity. So the domain of that function is from negative infinity up to infinity. And what we know is for the values of x less than 2/3, so I can show 2/3 somewhere there. For the values of x less than 2/3, the function is increasing. Okay, function is increasing. Increasing means going up. These are the values less than 2/3. Over there, the function is increasing, positive derivative. Function is going upward, like that. Okay. Now let's see where it is decreasing. Okay, for the function to be decreasing, the derivative must be negative. So negative 6x plus 4 is the derivative. That must be less than 0. Now, if you subtract 4 on both sides, we get 6x is less than negative 4. And if we divide by negative 6 on both sides and reduce the fraction, we get x is greater than 2/3. That means for the values of x more than 2/3, okay, the function is decreasing. Okay. Now, if you want to write this in the interval form, this is completely fine. You can also write it as, if you look from the graph, here it is increasing. So it is increasing from negative infinity up to 2/3. Okay, you can also use the parenthesis and write the interval. Now, what we found here is for this interval from 2/3 up to infinity, greater than 2/3 means 2/3 up to infinity, the function is decreasing because the derivative is negative. Meaning of that is here the function is going down like that. Okay, so the function will have the extreme value here. So at 2/3, the function is, this side it is increasing, that side it is decreasing, means here we have the maximum value. So that is what is asked in the second part. Find the local maximum and minimum value of the function. So only local maximum is possible here. So we say that f of x has local maximum. Okay, local maximum at x equal to 2/3. Okay, at x equal to 2/3, the function has the local maximum value. And that maximum value is, we can write f max is equal to the value of the function at 2/3. So technically, we have to plug in 2/3 into the given function. So it will be negative 3 times 2/3 squared plus 4 times 2/3 plus 1. And if we simplify this, we should get 7/3. So the maximum value of the function is 7/3. Okay, that is the maximum value of the function, and it occurs at x equal to 2/3. So this is how we can use the first derivative. So in this one, we use the first derivative. Okay, we can use the first derivative to find the maximum value of the function. If the minimum value occurs, then we can also find the minimum value using the first derivative. Remember, to find the maximum or minimum value using the first derivative, we can use this diagram that I have drawn here, which is also called the sign chart. So we can use the sign chart, and hence we can determine where the function is maximum and where it is minimum. Okay, that is our third example. Let's proceed to fourth example. Okay, here is the fourth example. We have to find the local maximum and minimum. Okay, local maximum and minimum. You can have both values or just one value. So we have to determine that maximum and minimum value of this function, which is given here, using the second derivative. So we are using the second derivative test for this. We are not using that sign chart. Instead, we are using the second derivative to determine whether the function has a maximum or minimum value, and what is that maximum or minimum value. So let's start with the given function. Here, the function is f of x equal to negative x minus 49 over x. Because we are using the second derivative test, let's find both first and second derivative. So this implies the first derivative would be derivative of negative x is a -1. And then derivative of negative 49 over x would be positive 49 over x squared. And the second derivative would be, we find the derivative of the first derivative. So derivative of -1 is 0, and the derivative of 49 over x squared is negative 98 over x cubed. So we got the first and the second derivative. Remember, the maximum or minimum value occurs at the critical point. Critical points are the points where the first derivative is undefined or zero. So before we get to that, if you look at this function, we know the domain of this function. So domain of the function is everything but zero, because if x is zero, the denominator would be zero, which is not possible. So remember that the denominator cannot be zero. Okay, one more time. Maximum and minimum value occurs where the first derivative is zero or undefined. So if you look at the first derivative, okay, first derivative will be undefined when x equal to zero, which is not in the domain. So I don't have to worry about that. All I need to know now is, where is this first derivative? Zero. So let's see. If the first derivative is equal to zero, then what I'm getting is this one, 49 over x squared minus 1 equal to 0. 49 over x squared minus 1 equal to 0. So that means 49 over x squared must be 1, because 1 minus 1 is 0. So if this is 1, then the x squared must be 49. So meaning of that is, this implies x squared equal to 49, or x equal to plus or minus 7. Those are the critical values. Okay, critical values are x equal to plus or minus 7. That means at this point, okay, for x equal to plus or minus 7, the function will have maximum or minimum value. In order to determine that, what we do is we try to plug in these values into the function. Okay, we try to plug in these values into the function. So if we plug in, let's see, into the second derivative. So let's plug in those values into the second derivative. Now, if you want to find the value of second derivative at positive 7, let's do it at negative 7 first. Okay, value of the derivative at negative 7, second derivative at negative 7. So we plug in here negative 98 over negative 7 cubed, right? We are plugging in here negative 98 over negative 7 cubed. So negative 7 cubed will be negative, and numerator is negative. Negative divided by negative means positive. So this value will be greater than 0. So you need to know the meaning of that. If the second derivative is positive, the function will have the minimum value at negative 7. So meaning of this is f of x is minimum. Okay, f of x is minimum at x equal to negative 7. And what is that minimum value? The minimum value is the value of the function at negative 7. So you plug in, okay, you plug in negative 7 into the original function. So it will be negative of negative 7. There is already negative, and x is negative 7. Negative of negative 7 minus 49 over negative 7. So you can see that, let me write here. So this implies f minimum, or the minimum value of the function, is equal to, so this will be positive 7. This one will also be positive. 49 over 7 is also 7. So that will be 7 plus 7, or 14. The minimum value of the function is 14. Okay, minimum value of the function is 14, and it occurs when x equal to negative 7, because when we plug in negative 7, we see that the second derivative is positive, that is minimum, and the minimum value of the function comes out to be 14. Now let's check the other point. We also have the other critical point, x equal to positive 7. So let's plug in positive 7. Okay, or let's plug in and see. Also, the second derivative at positive 7. Okay, second derivative at positive 7. We plug in here negative 98 over 7 cubed. Denominator is positive, numerator is negative. That means the value of the second derivative is negative. If the second derivative is negative, meaning of that is the function is maximum at 7. So we can say that f of x is maximum, okay? F of x is maximum at x equal to 7. Now we can find the maximum value of the function. So f max, the maximum value of the function, is the value at 7. So we plug in 7 into that function. So we get, if you plug in 7, that will be negative, and x is 7, minus 49 over x is 7, which is negative 7 minus 7, or negative 14. So the maximum value is negative 14. So this is how we can find the extreme value or local maximum and minimum using the second derivative test. So key here is you can find the maximum and minimum value, or the maximum or minimum value occurs at the critical point. The critical points are the points where the first derivative is 0 or undefined. So from there, you know where the maximum or minimum value occurs. But after that, what you have to do is you have to plug in these values into the second derivative. If the second derivative is greater than 0 or positive, the function will have minimum value there. And if the second derivative is negative, then the function will have maximum value there. So that's how we can use the second derivative test to answer the questions or to find the local maximum and minimum value. Okay, that is example 4. I hope you are enjoying so far. Now, time for example 5. See, identify the open interval on which the graph of the function is concave upward or concave downward. Assume that the graph extends past what is shown. Meaning of that is you can put the arrows at the end of these graphs, okay, so that you know that the graph continues forever, like that. Okay, so when we talk about concavity, when we say concave up, if you look from the graph, that means it should be the graph such that it is little bit it is cup upward. That means if you pour the water here, it should be able to hold the water. That is the nature of the graph. Okay, it can be like that, or it can also be like this. Okay, but if we talk about concave down, it should not be able to hold the water. It can be like that. We cannot pour the water here and it can hold the water. That's an easy way of looking at the graph. So if you see the graphs like that, that is the concave down. These two pieces that I've drawn here, concave down. These two pieces that I've drawn here, concave up. So in this graph, if you want to see where it is concave up, concave upward, let's see where it is concave upward. If I look at this piece, this is concave downward. This piece is also concave downward, but this piece here is concave up. And if you look at that graph carefully, you'll see that it is between -2 and +2, right? It is between -2 and +2. I can draw the vertical line here. So you can see that it is from -2 here. It goes up to there. So if I also draw the vertical asymptote there, you can see that in that interval between -2 up to 2, this piece of graph is concave upward. So the graph is concave upward from -2 up to 2. Okay, -2 up to 2. It is concave upward. And where it is concave downward, let's see. Concave downward. Okay. This piece is concave down here, this piece. So that is from -infinity up to -2. Okay, -infinity up to -2. And this piece here, this is also concave downward. And this is from 2 up to infinity. That is from 2 up to infinity. So in these two intervals, okay, in these two intervals, the graph is concave downward. And if you want to combine these two intervals, we can put a union sign in the middle. So what we did here is we look at the graph, okay? We look at the graph and we answer the question. So it's always easy to look at the graph and quickly answer the question. Okay, that is example 4. Now comes example 5. No, that was example 5, by the way. That was example 5. Now we move on to example 6. Okay, look like a long problem here. Consider the function, which is a rational function given here. We have to find the domain of the function. We have to find the local maximum and minimum value of the function. We have to find the inflection point. We have to write the horizontal and vertical asymptote, if any, interval on which the function is increasing and decreasing. And also, we have to give the interval of concavity of the function. So for this type of problem, you can solve it by using two different methods. You can find the derivative, second derivative, and then you can start answering. Or if you want to make it quick, what you can do is we can quickly sketch the graph of this function using calculator or any other graphing utility, and then look at the graph of that function and answer it. So what I'm going to do is I'm going to sketch the graph of that function and use that to answer the question. So let me quickly sketch the graph of that function. So the graph of the function will look like this. So this is the graph of the function. So now the first part is we have to find the domain of the function. So what is the domain of the function? So if we look at this function, okay, if we look at this function carefully, denominator of the function will be 0 when x equal to -2. That means the domain of that function would be everything, but it cannot be -2. Okay, it cannot be -2. That means if I want to write in interval form, it is from -infinity up to -2, and then from -2 up to infinity. I have to exclude that -2. So that is the domain of the function. Okay, that's your A. Now in B here, we are asked to give the horizontal and vertical asymptote of the function, if any. Now, horizontal asymptote is a rational function. For the rational function, the horizontal asymptote is always y equal to, if the degree of numerator and denominator is the same, it is the ratio of the leading coefficient. So you have 1 in the numerator, the leading coefficient is 1, 1 in the denominator. So 1 divided by 1 is 1. So the horizontal asymptote is y equal to 1. So meaning of that is, if you look at the graph carefully, you can see that as x goes to -infinity or as x goes to +infinity, the graph gets closer and closer to this horizontal line, which is at x equal to 1. That is the meaning of that. So this horizontal line is y equal to 1, horizontal asymptote y equal to 1. And then the vertical asymptote would be, let me use different color to write that. Vertical asymptote is x equal to the value that makes the denominator 0. So the value that makes the denominator 0 is a -2. So x equal to -2 is the vertical asymptote. So if we look at the graph carefully, you can see that we can draw a vertical line like that. Okay, we can draw a vertical line like that. So that is the vertical asymptote. So that is x equal to -2. Let me quickly change the color. Okay, let me do that. Okay, so you can see that this line in blue is the vertical asymptote, which is x equal to -2. And this horizontal line in black here, this is y equal to 1, which is the horizontal asymptote. So you can actually look at the graph and then you can easily tell which one is horizontal and vertical asymptote, or just by looking at the rational function also, you can write the, horizontal and vertical asymptote. Now, let's look at C. In C, we have to give the interval on which the function is increasing or decreasing. Now, if you look at this graph carefully, when you move from left to right, and from here, from -infinity up to -2, this graph is going always upward, meaning of that is it is increasing. So it is increasing from, okay, it is increasing from -infinity up to -2. Also, if you look at this piece here, as you go from left to right, from -2 all the way up to infinity, the graph is again going upward. So it is also increasing from -2 up to infinity. And if we want to combine these two intervals, we can write union sign in the middle. Okay, it is increasing here. It is increasing there. And it is not decreasing anywhere. It is only increasing, but it's not decreasing. Okay, it is only increasing. Now the next one, in D, we have to find the local maximum and minimum. So for the function to have a local maximum, okay, for the function to have a local maximum, the function should be increasing to a certain value, and after that it should be decreasing. In that case, you have the local maximum. But here the function is always increasing. It is not increasing and decreasing. That means there is no local maximum. For the function to be minimum, first the function should be decreasing and then it should be increasing. In that case, there will be minimum. Okay, in that case, there will be minimum. First, the function should be decreasing and then increasing. But here it's always increasing. Meaning of that is we don't have a local maximum or minimum. Okay, so this is not possible. There is no local maximum or minimum for that function. So that is the answer for B. It is not possible, not available, right? Now, let's look at the next part, part E. So in part E, we are asked to give the interval of concavity. When we say interval of concavity, meaning of that is where it is concave up and where it is concave down. So for this one, concave up, we have to write the interval for that. And we also have to write the interval where it is concave down. Concave down. So if you look at the graph carefully, this piece of the graph is concave up. Meaning of that is, it is concave up from -infinity up to -2. Okay, from -infinity up to -2. And if you look at this piece of the graph here, this is concave down, which is from -2 up to infinity, concave down from -2 up to infinity. And finally, we are asked to give the inflection point. Inflection point is the point where the concavity changes. You can see that it goes from -infinity up to -2, but -2 is not included. And then from -2 up to infinity, the concavity has changed. Here we have concave up and then concave down. Okay, concavity changes here, but that point does not exist. That means the inflection point does not exist. So there is no inflection point. There is no inflection point. There is no inflection point. So in this sixth example, what we did is, in order to answer the multi-part question like this one, we sketch the graph and we use the graph to answer the question. As I said earlier, you could have done the longer method. You could have gone through finding the first derivative, second derivative, whichever is relevant. You use that and then answer all those questions. But it will be much easier and faster if we can, sketch the diagram first using the graphing utility software, and by looking at the graph, answer the question. Okay, let's move on to the seventh example, which is similar to this one. See, this question also has a multi-part, just like in the previous one, and we are asked to answer all those questions. So what we are going to do is, we are first going to sketch the graph of this function. So let's sketch the graph of that function using the graphing utility software. The graph will look like that. The first part is, we are asked to find the domain of the function. Okay, domain of the function. You can see that the function is defined for everything from -infinity up to infinity. So that means the domain of this function is from -infinity up to infinity. You can technically plug in any value of x and this function is well defined. So that's why the domain of this function is from -infinity up to infinity. And if we look at B, we are asked to give the horizontal and vertical asymptote of the function. So you can clearly see that As x approaches to negative infinity or x approaches to positive infinity, the graph is not approaching any finite value. This is going all the way down to negative infinity on this side. This is going all the way up to positive infinity on that side. Meaning of that is there is no horizontal asymptote. Okay, and if you think of the vertical asymptote, there are no values of x at which the function is undefined. So technically there are no asymptotes. No asymptotes. Okay, there are no asymptotes. Now let's look at the next one. In C, we are asked to find the interval of increasing and decreasing. Where is the function increasing and where it is decreasing? That is what you have to find. Where is the function increasing and where it is decreasing? Because you have sketched this graph using the graphing utility software, you can see here that this graph is increasing all the way up to here, and from there it started decreasing. So we can find that value using calculator. So that value is, let me label it, okay? That value is negative 1,000. Negative 1,000, okay? That value is negative 1,000. So you can see that the function is increasing from negative infinity up to negative 1,000 and also from 0 all the way up to infinity. So we can say that the function is increasing on the interval from negative infinity up to negative 1,000 and then from 0 up to infinity. It is increasing there. But if you want to see where it is decreasing from this point all the way up to 0. That means from negative 1,000 up to 0, it is decreasing. So I can say decreasing, okay? Decreasing on the interval from negative 1,000, okay, up to 0. It is decreasing there. It's going down. So that is part C. Now, if you look at D, we are asked to give the local maximum and minimum value of the function. So you can see that the function over here, okay, around this point, if you look there, the function is increasing and then decreasing. That means the function is maximum at negative 1,000. So we can say that f of x or f max, okay, the maximum value of the function is at negative 1,000. Is at negative 1,000. Okay, the value of the function is maximum at negative 1,000. That means you can plug in negative 1,000 into that function. So it will be negative 1,000 plus 15 times negative 1,000 to the 2/3. And if you simplify that, you should get 500. 500. So meaning of that is the maximum value of the function is 500. Okay, the maximum value of the function is 500 that occurs here. So this point over here is negative 1,000, comma 500. And then for the minimum, you can see that the function is decreasing here and then increasing. If the function is decreasing and increasing, we have the minimum value there. The minimum value occurs at 0. So we can say that f minimum, the minimum value, is at 0. If you look at the graph, it is 0, the minimum value at 0, because this is 0, 0. You can directly write by looking at the graph, or you can plug in 0 into that function. So if you do that, 0 plus 15 times 0 raised to 2/3, that is also equal to 0. So the maximum value, the local maximum, okay, the local maximum is 500 and local minimum is 0. Maximum occurs at negative 1,000, minimum occurs at 0. So that is the fourth part, D. Now, if you look at E, in E, the question is, give the interval of concavity. So just like in the previous one, when we talk about the concavity, we have to write where it is concave up. I'll write CU for concave up and CD for concave down. Okay, we have to write where it is concave up and where it is concave down. So if you look at the graph carefully, okay, if you look at the graph carefully, you can find where it is concave up or concave down. So if you look very, very carefully, you see that this is concave down. Okay, this side also the graph is little bit concave down. So it is not concave up anywhere. So the concave up, it's not possible, right? This is not possible. But concave down, the graph is concave down from negative infinity up to 0, okay? Negative infinity up to 0, and also from 0 up to infinity. And also from here up to infinity, the graph is going a little bit concave down. So that's why this is where the graph has the concavity of concave down. Now, the last one is give the inflection point. Inflection point is the point where the concavity changes. Meaning of that is graph goes from concave up to concave down or concave down to concave up. There should be change in concavity. But for this graph, there is no change in concavity. It is concave down here, then again concave down. So that means the inflection point is also not possible. There are no inflection points there. Okay, I hope this is helpful. That is your 7th example. We have a few more to go. Let's move on to example 8. In example 8, we are asked to sketch the graph, okay, that satisfies these conditions here. So many conditions are given and we have to sketch the graph. So what I'm going to do is first I'm going to bring a graphing grid here so that I can use that to sketch the graph. Okay, now let's see. If you look at this graphing grid that I have here, I've scaled using 1. So -1, -2, -3, -4, -5 this side. Upward 1, 2, 3, 4, 5, and so on. Okay, few things here. For example, at -3, the derivative is 0. So meaning of that may be, okay, this is only the sketch, so it's not going to be a perfect graph. So maybe at -3, -1, -2, -3, okay, the graph may be, it can be up or down, I don't know, okay, -1, -2, -3, I don't know whether it's up or down, so I'm just going to put a dot somewhere there, and I say that the derivative is 0. Meaning of that is at this point, if we draw the tangent line should be horizontal. Okay, or this is where the concavity, I mean, the increasing or decreasing nature of the function changes. Okay, and same thing happened at 1. At 1 over here, maybe, I don't know, I'm just going to put a dot somewhere there. So over there also, the graph will change the increasing and decreasing nature, or the tangent line will be horizontal. Okay. Now let's find out. That is the first one. I use that. The graph is increasing on the interval from -3 up to 1. Okay, this was -3, by the way. Let me label that. That was -3. That was 1. So what they are saying is the graph is increasing from -3 up to 1. So -3 up to 1, the graph is going upward. So what I know is over here, the graph is going upward. The graph is going upward, but I don't know the concavity, so I'm just drawing a line for now, okay? So the graph is going upward over there from -3 up to +1. And then also from 1 up to infinity. Also from 1 up to infinity, even after that, the graph is increasing. I don't know the concavity, so I'm just drawing it like that. Okay. And on this side, they said it is decreasing from -infinity up to -3. -infinity, where I'm pointing, up to -3, it is decreasing. Decreasing means going down. Going down. See, decreasing, increasing, increasing, as it is said here. So we use that. Okay. Now comes the interesting part. So here they have the second derivative equal to 0. So wherever there is the second derivative 0, that these points are the inflection points. the points where the concavity changes. Okay, point where the concavity changes. So I'm going to label these points using, let's say, a green color. So at negative 5/3, okay, at negative 5/3, negative 1 point something, somewhere here, I would say. Over there, the concavity changes. That means if we look at this part of the graph, okay, when it arrives here, the concavity should change. That is the meaning of that. Concavity should change there, okay? And also the concavity changes at x equal to 1. X equal to 1 is here. So over here, concavity changes. Concavity also changes over there. So that is what we know. Concavity changes in those 2 points. Okay, so we take care of these also. We have labeled them. Now let's go here. The graph is concave upward. Okay, graph is concave upward from negative infinity up to 5/3. So here is negative infinity, 5/3 is here. Up to there, the graph is concave upward. So that means, let me modify this piece, which I draw as a straight line. Now I know that the graph is concave upward. So I have to draw it in such a way that it is concave upward, like that. So you can see that it is concave upward. And also it is concave upward up to 5/3. So let me remove this piece. Okay, let me remove that piece. And what I'm going to do is up to 5/3, the graph should be concave upward. Up to there, it is concave upward. I can draw it like that, or I can also do it something like this. Concave upward and then go up to there, like that. So you can see that it is concave upward, okay? And also it satisfies all the condition here. The tangent line will be horizontal as it is said here. And also it is concave upward from 1 up to infinity here. From 1 up to infinity, this piece is also concave upward. So let me redraw that, showing a concave upward nature there, like that, concave upward. And what is it between negative 5/3 and 1? You can see negative 5/3 and 1, it is concave downward. So this piece should be drawn such that it is concave downward, like that. Okay, so this is the sketch. So the graph of the function y equal to f of x satisfying all these conditions would look something like that. Remember, this is not the graph that is drawn to scale. This is just the sketch. Okay, this is just the sketch. So it can be, if more information were there, it can be more accurate. But for now, this is just the sketch of the graph. So you can see that we can use the derivative, first and second derivative, the increasing and decreasing nature, and the concavity to sketch the graph of the function. This was very helpful once upon a time when we don't have the graphing utility software, but we are still using it so that we can understand the concept of the derivative, concept of the first and second derivative. What are the meaning of increasing and decreasing function? What are the meaning of concavity, so on and so forth. So in order to master those concepts, in order to demonstrate the proficiency of those skills, we still use this. Okay, let's move on to example 9. So here is example 9. This is the problem on linearization. Find the linearization of this function at x equal to -1. So we want to find the linear approximation of this function. So that means the value of this function and the function approximated using linear function will be exactly the same. So if you remember, the linear approximation L of x is equal to f prime a times x minus a plus f of a. That is the formula for the linearization. And then here we have the function. Let's quickly write down the derivative of this function. The derivative of this function will be -5 over 5x plus 4 quantity squared. So if you find the derivative of this function, you'll get that. Okay. And here I wrote a is this value at x equal to -1. So the value of a is equal to -1. Now let's plug in all those information. So linearization is equal to derivative of the function at a. So if you plug in -1 here, let's see what you get. If you plug in -1 times 5 is a -5 plus 4 is a -1 squared, that's 1. -5 over 1, that is -5. -5 times x minus a is 1. -1, so that becomes +1. And then f of a, if you plug in 1 into this function, that will be -1 minus 1. Now, if you distribute that -5, so -5x minus 5 minus 1. So the linear approximation Lx is equal to -5x minus 6. Okay, that is the linear approximation of the function. So if you want to estimate the value of this function around x equal to -1 using the linear function, this is that function. Now, what we are asked to do is, so see, find the linearization of the function. We got that. Then find the true values of the function and the approximate value of the function in the table here. So for the true value, the exact value, you plug in these values into that function. You can simplify this using calculator. So if you plug in -1.1 into this function, 1 over 5 times -1.1 plus 4, you will get negative, I'm just going to write those values, negative 0.667. That is the exact value of the function at -1.1. If you want to find the exact value of the function at -1.01, you plug in -1.01 for x into this function, and you will get negative 0.952. You can simplify using calculator. Similarly, if you go very close to -1, that is -1.001, you get negative 0.995. So these are the exact values. And here we want to see the approximate values. Now you'll see that the approximate value will be, closer to the exact value if we go closer and closer to -1. So -1.1, -1.01, -1.001, that means we are heading closer and closer to that -1. That means as we go down here, the value will be more and more accurate. That means the approximate value will start getting closer and closer to that. So if we plug in -1.1 into this function to approximate, we get -0.500. You can see that they are a little bit off. They are not that close. Now, if I plug in -1.01 into this function and simplify, we get -0.950. Now you can see that this is much closer to the exact value. And if we plug in this one into the function and simplify, we get -0.995, exactly the same value. So as we go closer and closer to the value around which the approximation or linearization is done, the approximate value will also be more and more accurate. If you go far from that center, then the value will also deviate. So that is the meaning of the linearization. It will help you to approximate the value of the function around the point at which the linearization is done. Okay, so that is your example number 9. Let's go to example 10. So here in example 10, we are asked to compute the values of dy and delta y for this function given x equal to 0 and delta x or dx is equal to 0.05. So if you look at the function, we have y equal to, let me write that function. We have y equal to e to the 3x plus 6x. We can find the derivative first, dy over dx is equal to, the derivative of e to the 3x is 3 e raised to 3x, and derivative of 6x is 6. And if we multiply on both sides by dx, we get dy equal to 3e raised to 3x plus 6 multiplied to dx. So that is the differential notation, okay, equivalent to that function. Now, in the first part, what we have to do is we have to find dy, okay, dy. So if you see that, if you look at this one, in order to find dy, all I need is the value of x and dx, which is given here. Value of x is 0 and dx is 0.05. So we can say that dy is equal to, we have 3 times e to the 3 times 0, because x is equal to 0, then plus 6 multiplied with dx, which is 0.05. And if we simplify this, you can see that e raised to 3 times 0 is e to the 0, which is 1. 1 times 3 is 3. 3 plus 6 is 9. So we get 9 multiplied to 0.05, or that is equal to 0.45. Meaning of that is we get dy equal to 0.45. Okay. So that is the first part. We are asked to find dy. We got it. Now the next one we want to find is delta y. Now if you remember from your textbook, delta y is equal to, what we know is delta y is equal to f of x plus delta x minus f of x. Okay, because delta y is change in the y value. That is the new y value minus the previous y value. That is the change in y value, which is equal to f of, we are doing all that for these values given here. So x is 0, 0 plus 0.05 minus f of 0, which is equal to f of 0.05 minus f of 0. And then f of 0.05 means you plug in 0.05 into this function. Okay, let me show you there, which is e raised to 3 times 0.05 plus 6 times 0.05. And then minus f of 0 means you plug in, f of 0 means you plug in 0 into that function. So it becomes e to the 3 times 0 plus 6 times 0, which is equal to, you can simplify this using calculator. You should get 1.4618, then minus, this is 0 and this one is e to the 0, that's a 1, minus 1. And if you subtract, it will be 0.4618. So meaning of that is the value of delta y is 0.4618. So this is how we can use the differentials to calculate the differential y and delta y. Quite simple example, okay? Always remember, if you want to find the differential dy, you use the derivative. You find the derivative and multiply on both sides by delta x to get that dy. But if you want to get the delta y, it is a change in the y value. So it's a final y value minus initial y value, which is f of x plus delta x minus f of x. If you can remember that, you can easily perform the calculation. 10th example. Now let's move on to 11th example, which is quite similar to the 10th, but the function is not given here. See, we are asked to use the differential to estimate this value, the fourth root. And we are asked to compare that with the exact value. So what we do is we try to take a function that is similar to this one, the function that looks similar to that. So let's take a function f of x equal to the fourth root of x. F of x equal to fourth root of x, which is same as x raised to 1/4. Then find the derivative. Okay, find the derivative dy over dx. The derivative would be, if you use the power rule, 1/4 will come in front and we reduce the power by 1. So negative 3/4. And if we multiply on both sides by dx, we get dy equal to 1/4 x raised to 3/4. If I want to make the positive exponent, I can take it to the denominator, and I'm multiplying on both sides by dx. So that is the differential notation that we can obtain. Once you obtain the differential notation, we want to find the value at this one. We want to find the fourth root of 1.1. So the values should be over here. The values should be, if we are doing this approximation at 1, say for example, this should be 1.1, or your change should be 0.1. So what I'm going to do is I'm going to write that using that change notation. Now, what we know is f of x plus delta x, that is your new y value, will be equal to the original y value plus the derivative in the differential form. Okay, so now if we plug in the values here, this will be f of x plus delta x is equal to f of x. We know that this is the fourth root of x. Okay, fourth root of x plus the derivative of the function. You can see the derivative of the function multiplied with dx, that is, which is dy in fact, right? Which is this one, or just that one, which is 1/4 times x raised to 3/4, then dx. Okay, that will help you to find the value. So let's continue here. So if I want to find the fourth root of that, fourth root is same as the value of the function at 1.1. So what I can do is I can find f of 1.1 is equal to, that means for x, I'm plugging in 1, and for delta x, I'm plugging in 0.1. Okay, that is equal to fourth root of 1. Okay, fourth root of x is 1. Let me write that here. Okay, fourth root of 1, that's fine. Plus 1/4 times, okay, 1/4 times x is 1, 1 raised to 3/4. And then we have this dx. Dx is the change, which is 0.1, 0.1. And we can simplify that. So this is fourth root of 1 is 1 plus 1/4. Denominator is 1/4 times 0.1, which is equal to 1 plus 1/4 of 1 is 0.025, or we get 1.025. So that means the approximate value. So you should know the meaning of that. So the fourth root of 1.1, okay, 1.1 is approximately 1.025. That is the approximate value of fourth root. That is the approximate value. Okay, approximate value of fourth root is 1.025. So you can see that you can use differential to approximate. In one of the examples before, we used the linearization to approximate. We can also use the fourth root or any other root for approximation. Or in this case, we have used the differential, by the way. We can use the differential to approximate. Also, we are asked to compare with the exact answer. So let's use calculator to get the exact answer. Using calculator, let's find the fourth root of 1.1. Okay, let me use my calculator. If I use it, I get 1.024113. So which is quite close to this one, 1.025 up to 2 decimal place. It matches. It matches up to 2 decimal places. So you can see that differential are also the powerful ways of comparing, approximating the values. Okay, so there are two ways to approximate the value. One, you can use the linearization to approximate. The other one is you can use the differentials to approximate the values. Okay, we are heading towards the last portion. Now we have two more examples remaining. This is the 11th example. Let's move on to 12th example here, which is related rate. See, the radius of a circle is increasing at the rate of 9 centimeter per minute. So see, this one, 9 centimeter per minute, is the rate at which the radius is increasing. That means dr over dt is equal to 9 centimeter per minute. Okay, we have to find the rate of change of area. Rate of change of area means dA over dt. Change in area with respect to time is how much when the radius is 3 centimeters. So here we are talking about the area of the circle and also the radius of the circle changing. So what we know is this. We know area of circle is equal to pi r squared. And if you differentiate this with respect to time, you get dA over dt equal to pi is a constant. And then the derivative of r squared, okay, derivative of r squared with respect to time will be 2r times dr over dt. And we are actually looking for dA over dt. So that means we can just plug in the values there. So dA over dt is equal to, okay, I can multiply 2 and pi, that is 2 pi multiplied to the radius. Radius is 3 centimeters. Okay, radius is 3 centimeters. And then dr over dt is given in the problem, which is 9. So that means if I simplify that using calculator, okay, if I simplify that using calculator, I would get approximately 169.6 centimeters squared per minute. Centimeters squared because that is the area. Okay, so that is how we can find or we can solve the related rate problems. It is not very difficult. All you have to do is you have to find the derivative and plug in the values. So this is the word problem from the related rate problems. Now the last one would be this one, where they have given the values. See, assume that x and y are both differential functions of t and are related by this equation. We have to find dy over dt when x equal to pi over 8, given that dx over dt equal to -4 at pi over 8. So just like in the previous problem, we start with the given function. In the previous one, we write the formula. So here what we have is y equal to cosine 4x. If you find the derivative here, we need dy over dt. So we have to differentiate with respect to time. So dy over dt, okay, dy over dt is equal to derivative of cosine 4x with respect to t. Derivative of cosine is negative sign. So negative sine 4x. And then we multiply by the derivative of inside function. Derivative of 4x with respect to time is 4 times dx over dt. We use the chain rule there. And then we are actually looking for dy over dt. So we just need to plug in the values. So this implies dy over dt is equal to -4 sine 4 times the value of x is given. Value of x is pi over 8. Pi over 8 multiplied to dx over dt is also given. Dx over dt is -4. So dy over dt is equal to -4 multiplied to, this is sine pi over 2, which is 1, multiplied to -4, or that is equal to 16. So the rate of change here, dy over dt, is equal to 16. The rate at which the x is changing is -4. The rate at which y is changing with respect to time is 16. So this is how we can solve some basic problems related to the applications of derivative. I know this is quite a long video, but you managed to watch all the way up to here. Thank you so much for doing that. And I hope you find this video very, very helpful.